Welcome back to the class on electrical machine. In this lecture, we are going to discuss about the starting methods of a three-phase induction motor. Whenever we are giving a three-phase supply to the stator winding of a three-phase induction motor, the rotating field is creating from the stator winding. There is a rate of change of flux linkage with the rotor conductor. The voltage will be induced in a rotor conductor. At the time of starting, the rotor current is very high because the slip of the induction motor is equal to the 1. Whenever the rotor current is higher, the stator also will be taking more amount of current because of the transformer. If you're not limiting that current, the stator winding will be burned. So, to start the induction motor, it requires a starter. The name itself, it is a starter. It is a one equipment that we are using at the time of starting of the induction motor. When the motor is running, starter will be bypassed between the supply and the stator of the induction motor. The three-phase induction motors are the self-starting due to the rotating magnetic field. At the time of starting, the suppose induction motor S equal to 1, so the rotor current is high. Due to the induction principle, the stator also draws a high current. The starting current of induction motor is nearly 6 to 8 times the full load current or the rated current. So it can damage the motor wire. So to limit the starting current, the starter is required. Classification of three-phase induction motor starter. The starters are classified into the 5 types: DOL starter, stator resistance or reactance starter, auto transformer starter, star delta starter, rotor resistance starter. The first four methods we can use for the both squirrel cage and the spring induction motor. The last method we can use only for the spring induction motor. Now we are going to see one by one. In each case, we are trying to develop a mathematical expression for the starting current as well as starting torque to the full load torque. DOL starter. DOL starter is nothing but a direct online starter. Nothing but at the time of starting, we are giving a full voltage to the stator winding of induction motor. The stator winding of induction motor is designed such a way that it can able to withstand the large amount of current taken by the induction motor from the supply for the less amount of time. Generally, we are using the DOS starter for the power rating less than the 5 HP of a induction motor. To find the relation between the starting torque to the full load torque, let us take the ISC is the per phase starting current taken by the induction motor at the time of starting. IFL is nothing but the per phase full load current taken by the motor at a full load. Now this is the torque expression for the induction motor. If we observe this torque expression, this quantity is nothing but a I square RSP into RR. Nothing but this is a rotor copper loss at the time of starting. R stands for the rotor, SP stands for the starting. Divide by S, nothing but a air gap power. The air gap power divided by the synchronous speed of the stator flux gives the torque developed in a induction motor. So the starting torque PST equal to, in place of sleep, then you have to take the 1. Starting torque equal to 1 by omega S IR ST square into RR by 1. Suppose if you want to find the torque developed at full load, then the slip value you have to take it as a full load slip. So the full load torque equal to TFL equal to 1 by omega S IR FL square into RR by slip at a full load. Now take the ratio between the starting torque to the full load torque. 1 by omega S, 1 by omega S gets cancelled, RR gets cancelled. So finally you are getting the T starting by T full load equal to IRST by IRFL whole square into SF. This is nothing but the rotor current at the time of starting and rotor current at the time of full load. Now finally you are taking the same expression here. T starting by T full load equal to IRSP square by IRFL whole square into SFL. This is the final expression which represents the relation between the starting torque to the full load torque in terms of a rotor. Now we are going to represent this rotor current in terms of a stator. If we neglect the no load current taken by the induction motor, the stator ampere turns equal to the rotor ampere. Stator ampere turns is nothing but IST into per phase number of turns in stator winding equal to IRST into per phase number of turns in a rotor winding. The same manner, if we take the volt amperes at full load, IFL into per phase number of turns in a stator winding equal to IRFL into per phase number of turns in a rotor winding. Now take the ratio between the 2 by 3. Then it is given the relation between the starting current taken by the stator winding to the starting current taken by the stator winding at a full load equal to rotor current at a starting divided by the rotor current at a full load. Already in the previous expression, the torque relation in terms of a rotor current. Now in place of rotor current, now I have to substitute this one. So finally we are getting the starting torque by full load torque equal to starting current taken by the stator winding of induction motor divided by the stator current at a full load whole square into slip of the induction motor. Now, at the time of starting, the slip of the induction motor is 1. If we neglect the no load current, this is the equivalent circuit of a induction motor. V1 is the voltage applied to the induction motor due direct online starter. The current taken by the induction motor is ISC. This is the RSC. This is XSC. This is RR. This is XS. We assume that the ratio of number of turns from the stator winding to the rotor winding is the unit. ISC is nothing but standstill current. ISC equal to the voltage divided by the equivalent impedance of this circuit. That is ZSC. Now the ZSC you can write it as a RSC plus RR plus J XS plus at the time of starting with a DOL starter, the starting current equal to standstill current taken by the induction motor. Now in equation 3, the starting current by full load current equal to standstill current divided by the P full load square into slip of the induction motor at a full load. Stator reactance starting method of a induction motor. In this method, we are using a three-phase variable reactor between the supply and the stator winding of induction motor. By varying this variable point, we can apply the reduced voltage to the stator winding at the time of starting so that it limits the starting current taken by the induction. Here, the line voltage we have taken is a root 3 V1. The voltage which is available here after the three-phase variable reactor, we have taken the root 3 X V1, where X is depending upon the variable point of a three-phase variable reactor. Suppose if this variable point is at the time of starting, then X becomes a 1. The variable point at the ending of the reactor, X value becomes a 0.8 at 0.9. So that it will apply the less amount of voltage to the stator winding of a induction. The starting current taken by the induction motor, ISC equal to XV1 by ZSC. This is nothing but a per phase voltage. This is the line voltage. So divided by root 3, we are getting the XV1 divided by ZSC. Nothing but a short circuit impedance of induction motor. So this is equal to V1 by ZSC becomes a ISC. So the starting current taken by the induction motor is a three-phase variable reactor becomes a X into IS. Starting torque with the full load torque, TST by T full load equal to IST by IFL whole square into SF. Now we substitute this value here, then we are getting the TST by TFL equal to X square into ISC by IFL SF. When the induction motor is starting with a stator reactance starter, starting torque will be decreased by X square time. In case of induction motor, the torque is directly proportional to the V square. Starting torque with a reactor starting divided by starting torque with a direct switch. This is equal to XV1 whole square by V1 square. The V1 square gets cancelled. We are getting the X square. In case of auto transformer starting method, we are using a three-phase auto transformer between the supply and the stator winding of induction motor. At the time of starting, by means of auto transformer, we are applying the less amount of voltage to the stator winding so that the current taken by the induction motor will be reducing. When the rotor is rotating, we are applying the rated voltage to the stator winding of induction. This is the circuit diagram of the three-phase auto transformer starter with a three-phase induction. This is the three-phase supply. This is the three-phase auto transformer. This is the stator winding of a three-phase induction motor. This is the rotor winding. Here, V1 we defined as a per phase voltage supply side. XV1 is nothing but a per phase voltage on a stator winding side. Here X is a variable which is depending upon where this variable point is placed. The starting current taken by the motor winding, that is equal to XV1 by ZSC. This is equal to XIA. Nothing but this voltage divided by the per phase impedance of a induction motor at the time of starting. If we neglect the losses in a transformer, input volt ampere is equal to output volt ampere. At input side, you have taken at the time of starting IST into V1 because V1 is the voltage applied to the primary winding of auto transformer. That is equal to X into V1 into XISC, where XISC is nothing but the current at a secondary side of an auto transformer. XV1 is nothing but a secondary voltage of a auto transformer, which is applied to the stator winding of a. Now here IST into V1 equal to X square into V1 IST. V1 gets cancelled. The starting current taken by the supply, that is equal to X square into IS. Nothing but the current taken by the motor is reduced by X time, but the current taken by the supply will be reduced by X square time if you use the auto transformer. Suppose in case of a DOL starter and reactor starter, supply current and motor current is same. But in case of auto transformer, motor stator winding current and supply current will be different. That is the advantage of a starting of induction motor by means of a auto transformer starting. Now here, this is the general expression. Starting torque to the full load torque. The starting torque with a auto transformer, the full load torque with a auto transformer starter. That is equal to per phase starting current in motor winding divided by per phase motor current at a full load whole scale into slip of the induction motor at a full load. The per phase starting current taken by the motor with the auto transformer starting, that is equal to X into ISC whole scale divided by IFL whole scale into SFL. The per phase starting current can be included in the above equation. We know the relation between the ISC equal to ISC by X square. So in place of ISC, we substitute the ISC by X square whole square. To simplify this above equation, then we are getting the T starting by T full load, that is equal to 1 by X square into ISC square by IFL whole square into SF. Now this is the relation between the starting torque to the full load torque in terms of a starting current taken by the motor and full load current taken by the. Now we are finding the ratio of starting torque to the full load torque in terms of a starting current and standstill current. We know the relation here. Again, we have taken the same expressions. The starting torque by full load torque equal to 1 by X square. IST square we are writing as a IST into IST. In one IST, we are writing as a X square into IST because we know the relation between the starting current to the standstill current. So X square into IST into IST. Now you simplify this one. X square gets cancelled. Finally, you are getting the starting torque to the full load torque with auto transformer, that is equal to standstill current into starting current taken by the induction motor with auto transformer divided by square of the full load current into slip of the induction motor at a full load. So the three expressions are same only. The first expression is representing the starting torque to the full load torque in terms of a standstill current and full load current. The second expression is representing the starting torque to the full load torque in terms of a starting current taken by the induction motor with the auto transformer and full load current taken by the induction motor. The third expression is representing the starting torque to the full load torque in terms of a standstill current and starting current taken by the induction motor at the time of starting with a auto transformer. We know that the torque developed in induction motor is directly proportional to the V scale. The starting torque with auto transformer divided by the starting torque developed in the same induction motor. If we start with a direct online starting method, that is equal to X into V1 square by V1 square. V1 square gets cancelled. Finally, we're getting that. So from this equation, we can say very easily that starting torque developed in induction motor will be reduced by X square times the torque developed in induction motor if it is started with a DOL start. In case of star delta starter, the stator winding is connected in a star at the time of starting. So the per phase voltage applied to stator winding will be reducing. The stator current also will be reduced. When the speed of the motor is increases, now again the same stator winding will be connected in a delta. So this is the circuit diagram for the star delta starter. This is the three-phase supply. This is the TPS switch. This is the stator winding. This is the A phase, B phase, C phase. This is the starting terminal, this is the finishing terminal. Again, this is starting terminal, this is the finishing terminal. This is the starting terminal, this is the finishing terminal. Again, this is the TPS switch. The second side of the TPS switch is short circuited. Again, this side of the TPS switch is connected to the A phase and B phase and C phase respectively. So this is the electrical wiring diagram for the star delta. Let's take the VL the line voltage. The starting current taken by the induction motor when the stator winding is connected in star, that is represented with a ISTY equal to VL by root 3 into ZS. So when the stator winding is connected in a star, the phase current equal to the line current. Suppose if the stator winding is connected in delta, if you find the how much is the starting current taken with induction motor, IST delta equal to VL by ZS. This is the phase current. Suppose if we find the line current, then the line current equal to root 3 times this value. That is becomes a root 3 IST delta. Now we are going to take the ratio between the starting current taken by the induction motor when the stator winding is connected in a star and the starting current taken by the induction motor, stator winding is connected in a delta. IST by Y equal to IST by delta. This simplify means 1 by 3 times. Nothing but when the stator winding is connected in a star, the starting current taken by the induction motor will be decreased by 1 by 3 times the starting current taken by the induction motor. The same stator winding is connected in a. Suppose let we take the 100 amperes is the current taken by the induction motor when the stator winding is connected in a delta. At the time of starting, the same stator winding is connected in star. It will take the 33.33 amperes. It will take very less amount. We know that the torque developed in induction motor is directly proportional to the V square. Starting torque with a star delta starter divided by the starting torque with a direct switching on the delta connected stator winding. Now substitute those two values here. You're getting the 1 by 3. The starting torque developed in induction motor if the stator winding is connected in the star, it will be reduced by 1 by 3 times the starting torque developed in induction motor. Same induction motor, the stator winding is connected in a delta. The starting torque with a star delta starter to the full load torque with a stator winding in a delta by omega S IST by Y whole square into RR by 1. This is the full load torque. So the same expression, the slip value you take it as a SFL. The same manner, the current also you take it as a full load current 1 by omega S into IFL delta whole square into RR by SF. Now take the ratio between these two expressions. The starting current taken by the induction motor star equal to 1 by 3 times the starting current taken by the induction motor. The winding is connected in a delta. Now we have to in this place we have to substitute this one square divided by IFL delta whole square into SF. If you simplify this expression, we are getting 1 by 3 into ISC delta by IFL delta whole square into. With the help of the rotor resistance starter, at the time of starting, we are adding external resistance into the rotor circuit so that the rotor current will be reducing. Due to the induction principle, the stator current also will be reduced. This is the circuit diagram for the rotor resistance starter. This is the stator winding. These are the step rings and brushes. The brushes are connected to the external resistance. This method we can use only for the step ring induction motor because in case of step ring induction motor only there is a provision to add external resistance. We can't apply this method for the squirrel case induction. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of the YouTube channel so that I'm always welcome to answer all your